What if I told you that right now, at this very moment, there's a telescope floating 1 million miles away from Earth, and it just took a photograph of another world? Not an artist's illustration, not a simulation, a real image, a real planet. A world that exists in the darkness of space, orbiting a distant star, completely outside our solar system. And here is the thing that should stop you cold. Scientists are not just seeing this planet, they are beginning to read it. Its atmosphere, its chemicals, its temperature. And what they found, nobody was prepared for. Stay with me, because this changes everything. Picture this. December 25th, 2021, Christmas Day. While most of the world was unwrapping gifts, NASA was doing something far more extraordinary. They were launching the most powerful space telescope ever built into the cold, silent void of space. The James Webb Space Telescope, named after a former NASA administrator who helped shape the Apollo era, was about to begin a journey that no human-made object had ever taken before. It took 30 years to build. It cost $10 billion. It involved the combined intellectual firepower of NASA, the European Space Agency, and the Canadian Space Agency. Over 10,000 scientists, engineers, and technicians dedicated years of their lives to making it real. And when it finally lifted off on that Ariane 5 rocket from French Guiana, the entire scientific world held its breath. The deployment alone was a nerve-wracking miracle. Webb had to unfold itself in space like a giant origami structure. A gold-coated mirror nearly 7 meters wide, a sunshield the size of a tennis court, and a collection of instruments so sensitive that even a single degree of temperature change could compromise everything. Engineers had built in over 300 single points of failure. Any one of them could have ended the mission. Every single one had to work perfectly, in sequence, in the vacuum of space, with no possibility of repair. They all worked. By January 2022, Webb had reached its destination, a gravitational sweet spot called the second Lagrange point, or L2, located about 1.5 million kilometers from Earth. There, shielded from the heat of the sun, Earth, and Moon by its massive sunshield, Webb began cooling down to its operating temperature of minus 233 degrees Celsius, nearly as cold as absolute zero. Because the universe Webb was about to study, the infrared universe, is a universe of heat. And to see that heat, the telescope itself had to be almost perfectly cold. This is the machine that would change what we know about the cosmos. And one of its greatest achievements, one of the most profound things it has done, is something that sounds almost impossibly simple when you say it out loud. It took a picture of another planet. Before we get to the image itself, you need to understand something. You need to understand why this is so difficult that for decades, scientists thought it might be practically impossible. Imagine you're standing in the middle of a massive field at night. In the distance, miles and miles away, someone has turned on a lighthouse, an enormously bright lighthouse blazing with light in every direction. And right next to that lighthouse, just a few feet away from it in your field of view, there's a tiny firefly, blinking, barely visible, struggling to exist in the overwhelming glare of the lighthouse. That is the challenge of imaging an exoplanet. The star is the lighthouse. The planet is the firefly. And the distance between them, from our perspective here on Earth, is almost nothing. The planet SHIP 65426b, for example, one of the first exoplanets Webb photographed, is 10,000 times less bright than its own star. 10,000 times. From the perspective of a telescope billions of miles away, that star and that planet look almost like they are sitting on top of each other. For most of human history, we could not even confirm that other planets existed beyond our solar system. The first confirmed detection of an exoplanet around a sun-like star did not come until 1995. And for years after that, we only knew these worlds existed because of indirect methods, detecting the tiny wobble a planet creates in its star's motion, or the slight dimming of starlight when a planet passes in front of it. We were inferring their existence, like a detective reading footprints without ever seeing the person who made them. Direct imaging, actually photographing a planet, requires blocking out the overwhelming blaze of the parent star. And that is where Webb's coronagraph comes in. A coronagraph is essentially a tiny mask inside the telescope that blocks out the central disk of a star's light, creating a kind of artificial eclipse. This reduces the star's glare dramatically, allowing the sensitive instruments to detect the much fainter light coming from a nearby planet. The Hubble Space Telescope had attempted this and succeeded in a handful of cases. But Webb's coronagraphs are more refined, more powerful, and operating in infrared wavelengths where young planets, which glow with the residual heat of their formation, shine far more brightly. And so the stage was set. The most powerful space telescope ever built, armed with technology designed specifically to see past the blinding glare of distant stars. The universe was waiting, and the first image was about to be taken. The planet has a name that sounds more like a file code than a world, HIP P65426b. But do not let that clinical designation fool you. This is a real place, a genuine world floating in space about 385 light-years from Earth, orbiting a young star in the constellation Centaurus. It is a gas giant, 6 to 12 times the mass of Jupiter, and it was first discovered back in 2017 using the European Southern Observatory's Very Large Telescope on the ground in Chile. But what that ground-based observation could capture was limited. Webb was about to do something far more revealing. Using two of its most powerful instruments, the near-infrared camera, known as NIRCam, and the mid-infrared instrument, known as MIRI, Webb photographed HIP 65426 bets across multiple wavelengths of light. The images came back looking different depending on the filter used, because different instruments capture different kinds of light. But in each image, there it was, a small, glowing dot, a world, a planet beyond our solar system rendered visible for the first time in unprecedented detail. Sasha Hinckley, an associate professor of physics and astronomy at the University of Exeter, and the principal scientist on the international team studying this exoplanet, called the moment pivotal, not just for Webb, but for the entire field of astronomy. And Aaron Carter, a postdoctoral researcher at the University of California, Santa Cruz, who led the analysis of the images, captured the feeling that every astronomer on the team shared, the profound sense that this was just the beginning. HIP P65426b orbits its star at a distance roughly 100 times greater than the distance between Earth and the Sun. That enormous orbital distance is what made imaging it possible. It meant the planet was far enough from its star's blinding glow that Webb's coronagraph could do its job. But even so, the technical feat required to pull this image off was staggering. Webb's ability to suppress the starlight was, in the words of the scientists involved, genuinely impressive. This was not just a photograph. This was a proof of concept. A demonstration that Webb could do what no telescope had reliably done before: peer into the darkness around distant stars and pull out the faint light of orbiting planets. And if it could do it for a HIP 65426z, it could do it for others. Younger planets, smaller planets. Perhaps, one day, planets that look a little more like home. Then came something even more extraordinary. Not just imaging a planet discovered by someone else, but finding a planet that nobody had ever seen before. In June 2025, a team of astronomers led by Anne-Marie Lagrange, an astrophysicist at the French National Center for Scientific Research, announced a discovery that rewrote the record books. Using Webb's mid-infrared instrument with its coronagraph, they had been staring at a young star called TWA-7, officially cataloged as CE Antlier, located about 100 to 111 light-years from Earth. This star is remarkably young, only about 6.4 million years old, and it is surrounded by a complex debris disk divided into 3 distinct rings of dust and rock, the cosmic leftovers of planet formation. Scientists had long suspected that the gaps in TWA-7's debris disk might be carved out by unseen planets. The logic is straightforward. When a planet orbits within a disk, its gravity clears away material in its path, creating lanes and gaps. Observing those gaps from Earth had hinted at something lurking there, but nobody had seen it directly, until Webb looked in June 2024. When the telescope stared at the TWA-7 system, it spotted something. A faint infrared-emitting source within a gap between the first and second of the star's 3 rings. Webb's instruments, operating in the infrared where young warm planets glow, had picked up a signal that looked nothing like a background galaxy, nothing like instrumental noise. It looked like a planet. The team ran simulations, modeling what the system would look like if a planet of a certain mass occupied that gap. The simulated images matched what Webb saw almost exactly. What they had found was TWA-7b, a world with roughly the mass of Saturn, sitting approximately 52 times farther from its star than Earth sits from the Sun. Its temperature was measured at close to 120 degrees Fahrenheit, warm for a planet in the outer reaches of its star system, but consistent with a very young world still radiating the heat of its formation. The study was published in the prestigious journal Nature. Here is why TWA-7b is remarkable beyond the simple fact of its discovery. It is the lowest mass planet ever directly imaged. Period. Every other planet that had been photographed through direct imaging was heavier, often dramatically so. Getting to Saturn mass is a breakthrough, because it tells us that Webb's instruments are now sensitive enough to detect smaller, lighter worlds than anything previously imaged. The path from Saturn mass down to Earth mass is still a long one, but Webb just took the first step, and the planet had never even been cataloged before. This was not a known world that Webb confirmed. This was a genuine original discovery, pulled from the darkness by the telescope's infrared eyes. Webb had gone from photographing planets to finding them. But if TWA-7b is the discovery that rewrote the record books, it is K2-18b that has sent a quiet tremor through the entire scientific community. Because K2-18b is not just another distant gas giant. K2-18b might, and this word is doing a lot of work here, and that is intentional, might be something that no planet we have ever studied has been confirmed to be before. It might be inhabited. Now, let us be very careful here. The scientific process demands precision, and the scientists involved in studying K2-18b have been, for the most part, scrupulously careful with their language. But the signals that Webb has been finding in this planet's atmosphere are unlike anything ever detected on a world outside our solar system, and they deserve to be taken seriously. K2-18b is located 120 to 124 light years from Earth, in the direction of the constellation Leo. It orbits a cool red dwarf star in what astronomers call the habitable zone, the range of distances from a star where temperatures could allow liquid water to exist on a planet's surface. This is the Goldilocks zone, not too hot, not too cold, just right for water, just right, potentially, for life. The planet is about 8.6 times the mass of Earth and 2.6 times Earth's radius. It falls into a category called sub-Neptunes, planets with sizes between Earth and Neptune that do not exist anywhere in our own solar system. They are poorly understood, they are strange, and K2-18b is one of the strangest of them all. In 2023, Webb turned its instruments toward K2-18b and analyzed the starlight that filtered through the planet's atmosphere during transits. Those moments when the planet passes in front of its star and a thin slice of starlight threads through the outer atmosphere on its way to us. By analyzing how different wavelengths of light were absorbed during those transits, Webb's spectrographs could identify specific molecules. And what they found was remarkable. Methane, carbon dioxide, water vapor, an atmosphere rich in carbon-bearing molecules, consistent with what scientists call a Hycean world, a planet with a hydrogen-rich atmosphere covering a deep ocean of liquid water. The presence of methane and carbon dioxide combined, without a corresponding abundance of ammonia, is exactly the atmospheric fingerprint you would expect if there were a water ocean at the surface, because water oceans tend to absorb ammonia from atmospheres over time. But there was something else, something more controversial, something that, when the first paper was published, generated more discussion and more excitement and more heated debate than almost any astronomical discovery in recent memory. Dimethyl sulfide, DMS, a molecule that, on Earth, is produced almost exclusively by living organisms, specifically by phytoplankton in the ocean. Marine microorganisms consume certain sulfur compounds and release DMS as a metabolic byproduct. It is one of the primary contributors to the smell of the sea, and it is considered by many astrobiologists to be one of the most promising biosignatures, chemical signs of life, that we could look for in an exoplanet atmosphere. Webb detected a signal in K2-18b's atmosphere that was consistent with the presence of DMS. The detection was not ironclad. The signal sat at around 3 sigma confidence, which means there is roughly a 0.3% chance it was a statistical fluke. In most fields of science, a 3 sigma detection is taken seriously. But in physics and astronomy, the gold standard for a confirmed discovery is 5 sigma, which represents a 1 in 3.5 million chance of a false positive. So the scientific community did what it always does with bold claims. It looked again. It looked harder. In April 2025, the Cambridge team published updated observations that deepened the mystery. The methane and carbon dioxide signals remained strong. The atmosphere of K2-18b was confirmed to be rich in water, possibly comprising as much as half the planet's total mass, and the DMS signal persisted, though it had settled to approximately 2.7 sigma. Tantalizingly close, frustratingly just out of reach of a definitive conclusion. Then a NASA-led study pushed back. A different team reanalyzed the spectra using a different methodology and found what they described as inconclusive evidence. They pointed out that abiotic chemical processes, reactions driven by light, not life, could potentially produce DMS in a hydrogen-rich atmosphere. Laboratory experiments conducted in 2024 had demonstrated this under simulated exoplanetary conditions. DMS had even been detected in cometary and interstellar environments. The molecule, they argued, was not the unambiguous fingerprint of life that many had hoped. And yet, the signal is still there. The planet is still in the habitable zone. The atmosphere still has carbon dioxide and methane in the combination most consistent with a water ocean. The debate has not ended. It has deepened. And the researchers who study K2-18b are not walking away. They are planning more observations, more analysis, higher resolution spectroscopy that might finally push the DMS detection above the threshold of certainty, or rule it out entirely. This is science at its most electric, a signal that could be nothing, or could be everything. Not every world that Webb has examined is a candidate for life. Some worlds that Webb has turned its eye toward are the very definition of hostile, and studying them is just as important as studying the promising ones. In May 2026, astronomers made a different kind of first. They use Webb to directly study the surface of an exoplanet for the first time in history. Not the atmosphere, the surface itself. The planet in question was LHS 3844b, a super-Earth about 30% larger than our own planet, located nearly 50 light-years away. The result? LHS 3844b appears to be covered in basalt. Dark volcanic rock, rich in iron and magnesium, like the surface of the Moon or Mercury. No granite, no silica-rich crust, the kind of rock that forms on Earth through water-driven geological processes and plate tectonics. No sign of water, no sign of recycled geology, no sign of any of the processes that make Earth's surface dynamic and potentially life-sustaining. It is, in the words of the team, a dark, hot, barren rock, and the scientists studying it were not discouraged, because knowing what a hostile world looks like, and being able to read the surface geology of a planet 50 light-years away, is itself a revolutionary capability. Every barren rock Webb characterizes teaches us what to look for when we want to identify the exceptions. The worlds where the geology tells a different story. The worlds where the rocks have been changed by water, by life, by chemistry we have never seen before. Step back for a moment, because it is easy to lose the scale of what is actually happening here. Before Webb, we had confirmed the existence of thousands of exoplanets, almost all of them detected through indirect methods. We knew they were there the way you know there is a train coming before you can see it. You feel the vibration, you see the tracks, but you have never actually seen the train. Webb changed that. Webb can see the train, and not just the train, but the color of the train's windows, the smoke coming from its chimney, the passengers inside in silhouette moving around. The direct imaging of exoplanets gives us something that transit detection and radial velocity measurements simply cannot. It gives us light directly from the planet itself. And light carries information. Infrared light, in particular, carries the molecular fingerprints of whatever is present in a planet's atmosphere. Every molecule absorbs and emits light at specific wavelengths, like a cosmic barcode. Webb reads those barcodes. By 2026, Webb had directly detected atmospheres on multiple worlds. It had found carbon dioxide on a hot Jupiter in its first weeks of operation. It had mapped the three-dimensional weather patterns of gas giants. It had found a planet with an atmosphere so exotic, filled with helium and carbon, with clouds made of soot and possibly diamonds forming in its interior, that the scientists who discovered it said, and this is not an exaggeration, that no known theory could explain how such a planet could exist. That planet is PSR J232650b, announced in January 2026. It orbits a neutron star, a city-sized object with the mass of our Sun, spinning rapidly and blazing with radiation. The planet has a mass comparable to Jupiter, but the gravitational pull of its neutron star companion stretches it into an elongated lemon-like shape. It completes a full orbit in under 8 hours. Its atmosphere is dominated by helium and carbon, and astronomers believe the carbon could be compressed under the planet's intense internal pressure into actual diamonds. It is a world that should not exist by any model of planetary formation currently available. And yet Webb found it, and now we have to rethink what we know. This is what Webb keeps doing. It is not just filling in blank spaces on the map, it is revealing that the map itself was wrong. So where does this go from here? What does the future look like now that we can actually see other worlds? The James Webb Space Telescope has enough fuel to operate well into the late 2030s. Its mirror and instruments, after more than 3 years in space, show no significant degradation. It is in excellent health, and its scientists have barely scratched the surface of what it can do. The TRAPPIST-1 system is high on the agenda. 7 Earth-sized planets, several of them in or near the habitable zone of their star, located about 40 light-years away. Webb has already begun characterizing their atmospheres, and early results have ruled out thick hydrogen atmospheres on the innermost planets, which is important, because rocky, Earth-like worlds are expected to have thin, secondary atmospheres rather than the puffy hydrogen envelopes of gas giants. Finding the absence of a hydrogen envelope is the first step toward finding a terrestrial atmosphere. The search is ongoing. K2-18b will continue to be observed. More data, deeper observations, higher signal-to-noise ratios. If DMS is truly present in that atmosphere at the levels the Cambridge team believes, eventually the evidence will accumulate past the threshold of certainty. And if it does, if that 5 sigma confirmation ever comes, it will be the most consequential scientific announcement in human history. Not a candidate, not a hint. A real confirmed biosignature on a real alien world. Beyond Webb, the next generation of ground-based telescopes is being built. The extremely large telescope in Chile, with its mirror stretching 39 meters across, is expected to come online in 2028. With that kind of aperture, combined with advanced adaptive optics systems that correct for the blurring effects of Earth's atmosphere in real time, astronomers expect to directly image planets that are smaller and closer to their stars than anything Webb can currently see. Rocky, potentially Earth-like planets. Worlds where you could not only detect an atmosphere, but begin to map its composition across the planet's disk. And then there are the future space telescopes being planned at NASA and ESA. Concepts designed specifically for the detection and characterization of Earth-like worlds. Missions that would complement Webb's infrared vision with the ability to observe in ultraviolet and optical light, searching for oxygen. One of the most compelling biosignatures of all, a molecule that is so chemically reactive that it tends to disappear from atmospheres, unless something, life, is continuously replenishing it. The puzzle is being assembled, piece by piece, planet by planet, image by image. We are not there yet. We have not found the confirmation we are looking for, but we are measurably, verifiably, scientifically closer than we have ever been. Let us come back to that image, the one at the heart of this story, the picture of another world. There is a reason it matters beyond the science, a reason that goes beyond the spectra and the coronagraphs, and the sigma confidence levels and the molecular barcodes. It is the same reason the first photographs of Earth taken from space, the blue marble, the pale blue dot, had a cultural and emotional impact that transcended astronomy. We are a species that needs to see things to truly believe them. For decades, scientists could tell us that planets orbited other stars. The mathematics was certain. The indirect evidence was overwhelming. But it was abstract. It was a wobble in a graph, a percentage point dip in a light curve. It did not feel real. You could not point at it and say, there, that is a world. Now you can. When Webb returned those images of HIP 65426b, that faint dot of infrared light glowing against the darkness of space, something shifted. The universe became larger and simultaneously more comprehensible. Out there, 385 light years away, is a planet. It has weather. It has mass. It exists in 3 dimensions in real space right now while you're reading this. Webb saw it. And through Webb, in a very real sense, we saw it too. And when TWA 7b was found, a planet that nobody knew existed, pulled from the darkness by an infrared telescope and a coronagraph and 3 years of patient science, it was a reminder that the universe is not stingy with worlds. Planets are not rare. Planets are everywhere. And for every one we have found, there are countless others we have not yet looked for. And K2 18b, that warm, water-covered world, 120 light years away, with its methane and carbon dioxide and its tantalizing whisper of dimethyl sulfide in the air. That planet is asking a question that human civilization has been asking since we first understood what the stars were. Are we alone? And right now, in this moment in history, for the first time, we have a telescope that might be capable of answering it. We do not have the answer yet, but we are listening. More carefully, more precisely, more powerfully than ever before. If you made it this far, you already understand why this matters. The James Webb Space Telescope is not just a scientific instrument. It is humanity's eye, pressed against the glass of the universe, squinting into the darkness, trying to see if anything is looking back. The images it has returned, of HIP 65426b, of TWA 7b, of the surface of LHS 3844b, of the chemical fingerprints drifting in K2 to 18b's alien sky, are the first frames of a story we are only just beginning to tell. The universe is full of worlds. Webb is showing them to us, one image at a time. And somewhere out there in the vast dark between the stars, there may be a world where, right now, something is looking up at its sky, wondering the same thing we are. We are not done looking. We have barely started.